In the previous video, we talked about Dalton's law of partial pressures, which says that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the gases that make up the mixture. In this video, I'd like to go a bit further and talk about how the partial pressure of a gas is related to the mole fraction of that gas in a mixture. Well, let's start with some basics. If we have a mixture of gases, the total number of moles of gas in the mixture is equal to the sum of the moles of each component. For simplicity, let's assume that we have two components, A and B, so the total number of moles in the mixture is equal to the moles of A plus the moles of B. Now, let's also remember that we are assuming ideal behavior, so the moles of any gas will be equal to the product of the pressure and volume divided by the product of the gas constant and the temperature. Now, what do we mean by mole fraction? The mole fraction of a component in a mixture is a way of expressing the composition of the mixture, and it is simply defined as the ratio of the moles of that component to the total number of moles. The symbol that we use to represent mole fraction is the uppercase Greek letter chi, which looks kind of like a scripty looking X, but it's not pronounced X, it's pronounced chi. So chi sub A refers to the mole fraction of A in a mixture, which is simply equal to the moles of A divided by the total moles. Correspondingly, the mole fraction of component B is equal to the moles of B divided by the total moles. And keep in mind that the sum of the mole fractions of all of the components in a mixture, in this case the mole fraction of A plus the mole fraction of B, must be equal to 1 exactly, because they add up to 1. Now, if you're calculating the mole fraction, don't be fooled by the word fraction. We express it as in decimal notation to the correct number of significant figures. Now, since we're dealing with gases here, we can write an expression for the mole fraction of component A by substituting in expressions for the moles of A and the total moles based on the ideal gas law. So the moles of A will simply be the partial pressure of A times V over RT. And the total moles will simply be equal to the total pressure times V over RT as well. As we can see, V, R, and T cancel, and we simply get that the mole fraction of A is equal to the ratio of the partial pressure of A to the total pressure, which makes perfect sense. Okay. And by rearranging, we can see that the partial pressure of a component is simply going to be equal to the product of its mole fraction and the total pressure. So I can rewrite this as saying the partial pressure of component A in this mixture will be equal to the mole fraction of A times the total pressure, and the partial pressure of component B will be equal to the mole fraction of B times the total pressure. And if I had more components, I would include them as well. Now, to relate this to what we talked about in the previous video, let's see how this relates to the total pressure. So the partial pressure of A plus the partial pressure of B is going to be equal to the mole fraction of A times the total pressure plus the mole fraction of B times the total pressure. I can subtract out the mole fraction of A plus the mole fraction of B, factor out. Well, because we said before the sum of the mole fractions is equal to 1, that simply gives us that the sum of the partial pressures of A and B must be equal to the total pressure, which of course is Dalton's law of partial pressures. So let's see how this relates to a problem that involves partial pressures and mole fractions. So a mixture here is made up of 2.57 moles of argon and 6.87 moles of neon, and the total pressure exerted by that mixture is equal to 10.5 atmospheres. And the question is, what is the partial pressure of each component? Well, we know that the partial pressure of a component is simply equal to the moles of that component times RT over V. We know how many moles of each component we have, but we're not told the volume of the container or the temperature at which it's measured, so we can't measure that or calculate that. What we can use is the fact that the partial pressure of any component is going to be equal to the product of the mole fraction of that component times the total pressure. Since we're given the total pressure, and since we are given information that lets us calculate the mole fraction, let's simply do it that way. So the partial pressure of argon in this mixture will be equal to the mole fraction of argon times the total pressure. The mole fraction of argon is simply equal to the moles of argon divided by the total moles, which would be the moles of argon plus the moles of neon, all times the total pressure of 10.5 atmospheres. And that gives me 2.86 atmospheres of argon. I can calculate the partial pressure of neon in the same way. That will be equal to the moles of neon, 6.87 moles of neon, divided by the total moles, 2.57 moles of argon plus 6.87 moles of neon. I didn't explicitly calculate the mole fraction of each, but you could certainly do that. Keep in mind that each of the initial moles has 3 significant figures, so you would want 3 significant figures in your final answer. When I multiply that expression, which is the mole fraction of neon in the mixture, by the total pressure, that gives me 7.64 atmospheres of neon. And there is the answer to the question, which is the partial pressure of each gas in the mixture. So, how are we going to check our work to make sure we didn't make a silly mathematical mistake? Obviously, by seeing if the partial pressures that we calculated, that is the partial pressure of argon plus the partial pressure of neon, add up to the total pressure we started with. So, 2.86 atmospheres of argon plus 7.64 atmospheres of neon clearly adds up to 10.5 atmospheres total, which is the total pressure we started with. Now, let's switch to a different topic that's kind of related, but I'm going to include it in the video anyway, and that is, how do we calculate the average kinetic energy of a gas particle in a mixture? If we have a sample of a gas, let's assume for the sake of simplicity it's a single gas, at a given temperature that is greater than 0 Kelvin, then it has some kinetic energy. It is moving. That's part of the kinetic molecular theory of gases. Well, it can be derived, and you can look this up if you're interested, that the average kinetic energy of a particle of gas in a mixture is very simply related to the temperature. In fact, it's directly proportional to the temperature, and the equation you can see here, the average kinetic energy is 3/2 times R times T. Well, what is R? Well, we know R, the gas constant, is 0.08206 liters times atmospheres over moles times Kelvin. So the question is, how is that going to give us energy? Well, it turns out, it can be shown, and I'll show it in class because it's kind of cool, that multiplying pressure times volume actually gives you energy. Okay? It's pretty weird, but it actually works. Now, if we want to calculate our kinetic energy in an SI unit of energy, which would be the joule, then we're going to want to use R that has a different unit in the numerator, namely a unit of energy, or joules, and it turns out that that is equal to 8.3145 joules per mole per Kelvin. It turns out that R pops up all over the place in physical science. We will see R later in the course quite a bit, and we will see that if we want it in units of joules per mole Kelvin, we want to use a value of 8.3145. Okay? So, to calculate the kinetic energy, for example, of 1 mole of helium atoms at 298 Kelvin, I'll simply use my equation. The average kinetic energy is 3/2 R times the temperature, 3/2 times 8.3145 joules per mole Kelvin, times my temperature of 298 Kelvin. Obviously, Kelvin cancels, and that gives me an average kinetic energy, rounding to 3 significant figures, of 3,720 joules per mole of helium atoms. Okay? Now, what that means is that any specific helium atom in this mixture may not have exactly a kinetic energy of 3,720 joules per mole, but that the average of a large collection of particles will be exactly that. Now, the other thing that you notice is that I told you it's helium, but did that make any difference at all? No, because nothing about helium, other than the temperature that I gave you, is characteristic of this problem. What we see here is an important observation, which is that the average kinetic energy depends only on the temperature. It does not depend upon the identity of the gas particles, for example, the molar masses. As you'll see in the next video, other properties do depend on the temperature and on the molar mass, but for average kinetic energy, it is simply the temperature. Okay? And that's all for this video.